In this video, we're going to do another exam style question on impulse and momentum. In the question, we're told two particles, A and B, of mass 3m kilograms and 2m kilograms respectively, are moving towards each other on a rough horizontal track. Just before they collide, A has speed 3 meters per second and B has speed 5 meters per second. Immediately after the impact, the direction of motion of both particles has been reversed and they're both travelling with the same speed, which is v. In part A, we need to show that v is equal to 1 meter per second. So this is a conservation of linear momentum problem. If we do now a before and after sketch, we can go ahead and show that v is going to be equal to 1. So if we consider the before shot, we've got A just here, and then we've got B, which is going to be just here. So if we label these up, this now gives us the before shot. So before, and we can say now that the mass of A is going to be 3m, the mass of B is going to be 2m. If we now do an after shot, this is after the collision, we're going to have now A, which has got a mass of 3m, and again B, which has got a mass of 2m. So all we're doing is modelling these particles up to find the value of V. So we can write on now that we've got 3m and 2m. So 3m and 2m. Let's consider the speed of each before, and we can put these on. So we can see now that A has a speed of 3 meters per second and B has a speed of 5 meters per second. These are now travelling in opposite directions. So we can see that A is moving towards B and B is going to be moving towards A. And we can model this up like so. We have to be careful when we're working at the value of V to ensure that we're using the correct sign, whether it's positive or negative. So let's write this in, 3 meters per second, we've got 5 meters per second. We're told afterwards now the speed is going to be V and the direction of motion of both of these is going to be reversed. So we're going to end up now like so, and we can put these on. So let's do that, let's put these on. These are going to be V, so we'll put V. That's going to be v meters per second, and this one is going to be v meters per second. So we can state now the conservation of linear momentum, and we've looked at this in previous videos. The total momentum prior to the collision will be the same as the total momentum after the collision. Momentum is given as mass times by velocity. So if we consider before, we've got now 3m, so that's the mass of A multiplied by the velocity, and this is going to be a positive quantity, and we'll take that to be 3. We're going to add to that now the momentum of B. Has a mass of 2m and has a velocity of minus 5, as I've defined now the direction AB to be positive. We need to set this equal to the total momentum after the collision, so we're going to have 3m, that's the mass, multiplied by minus v. Then we add to that now the mass, which is 2m, multiplied by positive v, as we're going in the opposite direction. At this stage, we can state that this equation is independent of m. So we can see that we can divide through by m. So this is just going to leave us an equation with numeric values or values for v. So we're going to have 9, we're going to have minus 10, we're going to have minus 3v, and we're going to have plus 2v. So that gives me minus 1 is equal to minus v. Therefore, we can say at this stage that v is equal to 1 meter per second as required. So just using the conservation of linear momentum, as we've seen in all of the other tutorials, that becomes a fairly straightforward problem. We're now told the magnitude of the impulse exerted on A during the collision is 24 Newton seconds. We're asked in part B to find the value of m. What I'm going to do is just sketch this up. You certainly don't need to do this, but it might help your understanding. So what I'm going to do is have A before and after. So if I put these values on, let's just go ahead and do that. I don't think this is entirely necessary, but again, it might help with a bit of understanding. So what we're going to have then is the impulse. So this now is the impulse exerted on A by B. So let's go ahead and put this on. We've got now 3m and we've got 3m. Before we had this speed, this was going to be 3 meters per second, and now we've got 1 meter per second. If we consider impulse, impulse is the change in momentum, and we can write that as follows. Let's go ahead and write that. We can write now that I is equal to m, where m is the mass, multiplied by the final velocity minus the initial velocity. We're told now that the impulse is 24 Newton seconds. So I've got my 24 Newton seconds, and I can say at this stage now that 24 will be equal to the mass. Well, the mass is 3m. Then we're going to have the final velocity, which is going to be 1. So that's the velocity after the collision, minus now the initial velocity. Consider now that I've put the impulse to be positive from right to left. Therefore, this is going to be a negative value, and we can put in minus 3. So we've got 24 is equal to 3m, and then this is going to give me 4. So we can say 12m is equal to 24. So we can say from this stage now that m is going to be equal to 2. 24 divided by 12 gives me that m is going to be equal to 2. The next part says, given that the coefficient of friction between A and the track is 0.1, in part C we're asked to find the time taken from the moment of impact until A comes to rest. So we're now switching away from momentum and impulse, and we're going to be looking at Newton's second law. So let's go ahead and draw a quick sketch. So here's my sketch, and we can put on some information. We're going to use the constant acceleration equations, or SUVAT. So let's collect some information. So this is going to be my particle. So what I'm going to do is put down here SUVAT, and we'll build up this information. We know that the initial velocity is going to be the 1 meter per second. We know the final velocity is going to be 0 meter per second as it's coming to rest. We want the value of time, and we need to find either the acceleration or the displacement. I'm going to find the acceleration. Let's consider what we've got here. We know that m is 2, therefore we've got now a mass of 6 kilograms. If m is 2, we can say that this is going to be 6 kilograms. If we consider now the forces acting on the particle, we're going to have a normal reaction force. So that is going to be perpendicular to the rough surface, and then we're going to have now the weight acting down. So we can say that this is going to be r, or if you like, n, and this is going to be the weight. Weight is mass times gravity, so this is 6 Newtons. What we need to consider now are the forces acting horizontally, and we're going to have now the frictional force. The frictional force is going to be opposing the motion. So I'm taking now the motion to be from right to left. So we'll have this frictional force. So let's just put this here, the frictional force, and I'll put an acceleration which will ultimately be a deceleration now, and we can put that in this direction here. So let's go ahead and just label that up, and we'll call that A meters per second squared. So let's go ahead and just put that on, that's A meters per second squared. So what we're looking to do is find that value. If we consider that this now, we can say friction is limiting. So we can say friction is limiting. Therefore, from this, we can now say that F is equal to mu r. The friction is equal to now the coefficient of friction, which we've got here, which is mu, 0.1, multiplied by the normal reaction force. So if we write this out, we've got F is equal to 1/10 or 0.1 r. What we need to do is find r. So using Newton's second law on the particle, we'll consider now the vertical movement. There is none. So what we can say then is r minus 6g will be equal to 0. So r will be equal to 6g. So if we sub this in now, we can say that the frictional force is going to be now 1/10 of 6g, which is going to give me 3/5 g, or we could say 0.6g. Entirely up to you. So this now is the frictional force that's opposing the motion. If we consider Newton's second law now, we can find the acceleration. So using Newton's second law, we're going to consider now the horizontal motion. So what we have is the following. We know that this is F is equal to ma. So let's just write that here. F is equal to ma. So we've got now this frictional force, and that is going to be opposing the motion. So we can say minus 3/5 g will be equal to the mass, which is going to be 6 now. We've got 6 kilograms multiplied by the acceleration, which I've called a. So from this, we can see that we're going to get a negative value. So if I go ahead now and divide both sides by 6, that's going to give me minus 1/10 g is going to be equal to the acceleration. So now I've found the acceleration, and I can sub this in. So if you want, you can put minus 1/10 g. Remember, g is just 9.8. Let's just write this here. G is going to be 9.8. So if you wanted, you could say 0.98. It's entirely up to you. So if you want minus 0.98, and that's going to be meters per second squared. So what we want to do now is find the value of t. So using SUVAT, V is equal to U plus AT. We can simply go ahead and sub in. So 0 will be equal to 1, and then we're going to have now plus AT. So that's going to be minus 0.98T. So doing some rearranging, we can say now that T will be equal to, and then we'll have 1 over 0.98. So if we just put that through a calculator, let's go ahead and do that. We've got 1 divided by 0.98. That's going to give us now 50 over 49. Let's write this in. So T is going to be equal to 50 over 49 seconds. Or if you want to give that now to a decimal answer, let's put that there, 1.02 seconds. So 1.02 seconds, and that now is to 3 significant figures. So what we've done here is used a range of skills. Initially, we've looked at the conservation of linear momentum, we've looked at a bit of impulse, and then we've looked at Newton's second law. So when you come up against these questions in exams, sometimes they will be purely based on impulse and momentum, and then later on you'll use some of that information to find problems involving the dynamics of a particle.